My name is Melissa Farias.
My name is Cecilia Galindo.
And my name is Paulina Gonzalez.
And for this project, the purpose was to find the area under the curve of the graph of an original painting we had with different methods such as Riemann sums and also with integration. And in the end, we have to relate how the approximations, how different they were.
The first part of our project consisted on using the Riemann sums tool to get the area of under the curve of a paint we chose. We figured out that the more amount of rectangles you have, the more accurate the area under the curve gets.
And then in the second part, we plotted 10 points using the boundary of the area we wanted to find from the painting. We found a function, and then we graphed it and found the area using integration.
And now we're gonna show you our work. The painting we chose, we decided to put it in a grid line to have the exact points. We needed to determine where were the exact points, so we used this tool to help us locate each point. So in point 15, you know that it's 5 approximately. Then we used the Grammatica tool to plot the points that we searched and looked for in our previous mentioned tool. Here are the points we graphed. 14, 12, 10, all of these are the points we decided to graph.
Okay, so first we decided to use a technological aid to find the regressions to get the equation of the curve that contains the area. So we tried many different options. Like first we tried logistic, and then we saw that it fitted really good and it was very approximated to the points. And then we saw different ones like exponential, and then it was also really approximated. And finally we saw the sinusoidal function, and it was also really approximated. So in the end we chose of these 3D final functions since they were really good. After analyzing the 3 lines, we decided that sinusoidal was the best option since more points coincide with the line that it has.
So after Graphmatica gave us the function of the line, which is the sinusoidal, this one we are selecting, we wanted to compare it with the painting and how it will affect it, and we inserted the expression using the Desmos program. And here we can see how our area inspected was from 0 to 15, and the function actually goes through those points in our painting. And then to find the most accurate area, we use Graphmatica again and the integration tool to find the exact area from the origin to the 15 in the x-axis. And the area gave us positive 114.739. And so now, concluding what we saw in both parts of our project, we can see that what we saw in part 2, the integration procedure is more accurate than the Riemann sums. And this is because in the integration procedure, we used 2 exact points in the area we wanted to find under the curve. These ones being A0 and B15 in the x-axis. And in the Riemann sums, we used an indefinite amount of rectangles that didn't help with the accuracy.
So in our opinion, that's why we think that it was easier using definite integrals, because we calculated in a grid with the painting the exact points, and we developed the line according to those points and not by using squares above and below the line.
In comparison with both projects, we
in the first part of the project, with 23 rectangles, that it was the most exact one, we got an area of overestimation of 124 and underestimation of 101. And with this new tool we're using, with definite integrals, we got that the exact area from point A to B was 114.
And it is also true that technology and tools like Graphmatica helps us a lot to estimate the area correctly. ¿Me viste?
1 y 1.1
Pero-
1
Y 1.2.
y 3.4. Hasta. Ok. Y luego hacemos